Hello, welcome to topic 10.1 of the AP Chemistry Daily Videos. Today we will be discussing stovetops, gas, electric, and induction. In this video, we will focus on the detrimental effect of gas cooking and learn the difference between electric and induction stovetops. I'm Henry Gold, a student at Lake Forest Academy in Lake Forest, Illinois. First, let's discuss the dangers of gas-based cooking. Natural gas stoves emit 0.8 to 1.3% of the gas they use as unburned methane. The total US stove emissions are 28.1 gigagrams of methane per year. More than 3/4 of methane emissions measured originated during the steady state off condition, which means there must have been leaks. Additionally, health-damaging air pollutants such as nitrogen oxides are released into home air and can trigger respiratory diseases. So, how do electric stovetops work? Radiant electric cooktops have heated coils beneath a ceramic or glass surface. This heat radiates through the surface to heat the pan from the bottom. Electric is compatible with any kind of cookware, as long as it has a fairly flat base that makes contact with the glass surface. However, there is residual heat with electric cooktops, which results in burns, as it can be very difficult to tell if your stovetop is truly hot. Induction cooking relies on the principles of magnetic induction. Induction takes place when eddy currents are created from the presence of an oscillating magnetic field, as denoted by Faraday's law of induction. These induced currents dissipate heat by the Joule effect. Current flows in the cooking vessel due to the low resistance of the metal, with power dissipation given by power is equal to current squared times resistance. This process allows energy to go directly from the coil to the cookware without dissipating through the surface. As such, less heat is lost from inefficient thermal conduction between the heating element and the cookware, making the surface safe to touch. Induction cooktops are only able to couple with ferromagnetic cookware due to their high magnetic permeability and resistivity, such as cast iron and some alloys of stainless steel. Thus, modern induction cooking technology is not compatible with cookware made from glass, ceramic, aluminum, or copper. And in conclusion, for induction cooking, 90% of the energy consumed is transferred to the food, while only 74% is for electric and a measly 40% for gas. Induction cooking is also less likely to cause burns or fires than the alternatives because no heat is created without the ferromagnetic cookware. Additionally, over 70 cities or counties in California mandate electrified cooking for new construction, and hopefully more will come in the future. Thank you.
Hi, it's Bella, and today I'm going to talk about how hydrogen-boron fusion is the next big step in reversing the effects of global warming in our atmosphere. Here at the bottom of the page is the chemical equation of hydrogen-boron fusion. As you'll see, an isotope of boron is used in fusion, boron-11. You may be asking, what even is hydrogen-boron fusion? Hydrogen-boron fusion would ultimately mean the end for fossil fuels. Hydrogen-boron fusion is a safer and more efficient way of nuclear fusion and power. This is a good thing because people in today's society want a stable source of energy that will not turn off and is reliable. In comparison to nuclear fusion, which is based off tritium and deuterium fuels, which produce free neutrons and cause radioactivity and later decay, hydrogen and boron do not produce any neutrons and can hold up for decades, which is very dependable. Hydrogen-boron fusion mimics star energy power and requires a very high temperature that has yet to be replicated on Earth. However, a company called Tri-Alpha Energy has gotten very close, however it is still mainly in the future. In the process of hydrogen-boron fusion, no carbon or carbon dioxide is produced. It is very environmentally friendly and sustainable. Nothing is burned in hydrogen-boron fusion, which means that no carbon dioxide is produced. No greenhouse gases are produced as well, which warm up the environment because warm temperature gets trapped in the atmosphere. A fun fact is that hydrogen-boron fusion produces no neutrons and produces no radioactive waste as well. Real-life applications of hydrogen-boron fusion include the new BMW iX5 hydrogen-powered engine. This car will be emission-free and will last longer without refueling. This car will be more environmentally friendly than other electric cars, which still produce evaporative emissions. BMW stated that this car will be released as soon as 2025. Here are the sources that I use in this project. Thank you!
In modern days, many architects and construction companies pursue efficiency in the building process. They search for materials that were cheap, strong, and long-lasting. Cement was the answer, which made them use it without considering other side effects. As time passed, people started to recognize its enormous impact on our environment and realized it was time to change before it got too late. So I'll be explaining two possible alternatives of cement: hempcrete and graphene cement. As provided above, cement is one of the strongest pollutants. It harms both the ocean and the air. Cement produces sulfur dioxide, carbon monoxide, and nitrogen oxides, which are very harmful types of gas. Also, cement production consumes large amounts of water, especially threatening drought regions, and frequently leaches chemicals into the ocean. In 2015, 8% of global carbon emissions were solely based on cement production, and in 2022, 9% of water withdrawal was due to excessive cement usage. The first alternative is hempcrete. Hempcrete is a term that combines two words, hemp and concrete. It is concrete that uses hemp and lime as a prime ingredient, not cement. Hemp is a plant that only takes about 4 months to grow, and because it is a plant, it is very highly biodegradable. Lime produces 80% less carbon than conventional cement. Most importantly, hempcrete has a unique feature to sequester carbon through its life cycle. Other features of hempcrete don't fall behind compared to cement, such as insulating ability. However, hempcrete has some limitations in its application. Because it takes a long time to cure, hempcrete cannot be used for walls that handle heavy weights. Also, the porous structure of hempcrete sometimes creates a bad environment for the wall to be water resistant and deformed by itself like in the image above. Although there are disadvantages and more studies of applications are needed, the prospect of this substance is positive. Growing awareness of the environmental advantages that hemp possesses is acknowledged by many architects and companies. In the USA, for example, companies like Hemplot USA and Hemptexture are supplying hempcrete products encouraging the usage of eco-friendly material. Another alternative is graphene cement. Graphene cement is composed of graphene and cement. Graphene, a one-atom thick sheet layer of carbon, is the strongest man-made material. The experiment from the University of Exeter explains the advantages of graphene. It has substantial increases in compressive strength and flexural strength in concrete. Moreover, the inclusion of graphene prolonged the lifespan of concrete, allowing companies to reduce the production of additional cement. The experiment states that graphene cement will reduce 446 kilograms of carbon dioxide emission per 1 ton. As mentioned above, graphene cement exceeds every feature of the original cement. They are more rigid, flexible, and eco-friendly. However, one drawback is that graphene is only produced on large scales. Since this material is produced in thin layers at a time, it requires higher technology to manufacture graphene cement and combine it, which results in cost problems. Thus, the prospect of this material is very clear. The more technology improves, the more graphene cement will be used. Thank you for listening to my presentation. Let's keep building towards a future where our buildings show not just how smart we are, but how much we care about our planet.
You have probably seen these videos of giant geysers blasting thousands of liters of hot water in just a few minutes. Or perhaps you have swum in one of those natural hot water lakes, wondering where all of that heat comes from. Deep beneath the surface of the earth lies huge amounts of hot magma that reach temperatures up to 1400 degrees Celsius. This magma heats the underground water reservoirs, turning them into hot and steamy water. But here's the best part: the steam can be used to generate renewable energy, most commonly known as geothermal energy. Let's take a closer look at how it works. Hot water is pumped under high pressure from deep underground, ranging from 1500 feet to 10,000 feet below the surface. When the water reaches the surface, the pressure is dropped, causing the water to turn into steam. Then, the steam spins a turbine, which is connected to a generator, this way generating electricity. Used water is re-injected into reservoirs to prevent contamination and land subsidence, and once heated, can be reused again. Some water is lost to steam, so additional water is required to maintain reservoir levels. Geothermal energy has a huge potential that has not been used enough. In fact, it has been listed number 18th on the most effective ways to reverse global warming. If the global geothermal electricity generation would grow from around 0.66% today to 4.9% by 2050, it could reduce carbon dioxide emissions by 16.6 gigatons and save $1 trillion in energy costs over 30 years, or $2.1 trillion over the lifetime of the infrastructure. Moreover, according to the Geothermal Energy Association, 39 countries could supply a full 100% of their electricity needs from geothermal power. However, only 7% of the world's potential geothermal power has been touched. Now, part of the reason is the fact that prime geothermal conditions, where heat, fractured rocks, and water are found within a couple of miles from the surface, are only on less than 10% of the planet. On the other hand, new technologies have expanded the potential areas where geothermal energy could be obtained. For instance, scientists use a new technology called EGS, which uses the underground area where hot rocks are found but little or no water, by simply injecting water and fracturing the rock, thus creating pathways to absorb more heat. However, whether naturally occurring or pumped in, water and steam can have other dissolved gases, such as carbon dioxide, and even toxic substances, such as mercury, arsenic, and boric acid. Additionally, constant extraction of geothermal energy could result in soil subsidence, and even produce micro-earthquakes. In the end, geothermal energy must be utilized to reduce the reliance on fossil fuels and minimize the greenhouse effect. Government funding and public investing are needed to expand geothermal energy generation to its fullest potential, especially in places such as Indonesia, Central America, and East Africa, where the planet is the most active.
Hi all, I'm Sun, and today I'm going to talk about rooftop solar, concentrated solar, and solar water. So, what is solar energy? By definition, solar energy is a radiation from the sun capable of producing heat, causing chemical reaction to generate electricity. Solar energy has a lot of application in the world, such as rooftop solar, solar water, and a bigger and more industrial scale, concentrated solar. So, how does water solar work? First, the cold water goes through the solar panel to get heat up. Then, the water is transferred back to the tank and finally get distributed for usage. In case there is no sun, the water can be boiled by the boiler. The sun ray contain photon, and when they hit the solar module, the electron inside the solar module move, and an electrical current is created. This electricity is then traveled from the solar array to an inverter. The inverter takes the electricity, which is in DC or direct current, and turn it to AC or alternating current. Then the electricity is now ready for household use. However, this is only for personal use. For electricity production, high temperature solid thermal system called concentrated solar or CSP use group of mirror to concentrate solar energy on a center collector. This produces high enough temperature to generate steam, which is then turn a turbine, driving as a generator, and then create electricity. CSP is often found in desert where sunlight is abundant. To create electricity from coal, the Massachusetts Power Utility Companies use 0.846 pound carbon to create 1 kilowatt-hour of electricity. An average resident solar system is 9 kilowatt and would produce about 10,000 kilowatt-hour in a year. So, if we do the math, 10,000 kilowatt-hour times 0.846 equals 8,460 pounds of CO2, which is equivalent to a carbon emission of 432 gallons of gas, almost the amount of gas to fuel your car for the entire year. To look into the big picture, Boston Solar have installed over 4 million solar energy systems, totaling 33,000 kilowatt, which can generate more than 30 million kilowatt hour a year. And if we do the math, 30 million kilowatt hour times 0.846 equals 25,380,000 pounds of CO2 a year. That is equivalent to save 190,356 trees seedling growth for 10 years, 1,295,395 gallons of gas, 437,276 light bulbs switched to LEDs, and 26,653 oil barrels. Thank you for listening to my video.
Hi, I'm Matthew and I'll be presenting about electrical vehicles. What is the current problem? Cars that are using internal combustion engines are emitting enormous amounts of toxic gases such as carbon dioxide, nitrogen dioxide, carbon monoxide, and etc. Each car passenger is producing around 4.6 metric tons of carbon dioxide alone. Conventional vehicles that use either gasoline or diesel as its fuel contribute 10% of the world's carbon emissions. So how do we fix the problem of conventional vehicles? We can use vehicles that can run on alternative fuels, such as electricity. First, what are electric vehicles? It is a vehicle that can be powered by an electric motor, which derives its electricity from a battery that does not produce tailpipe emissions and is able to recharge through an external source. Here is a full diagram that shows the key components of an electric vehicle. Since we now know the components, how does it work? First, the vehicle gets connected to a charging station via using a plug to the charging outlet. Second, the traction battery pack gets charged and stores energy in the form of direct current power. Then, the auxiliary battery pack gets charged with direct current power from the traction battery pack to run vehicle accessories including headlights, audio, and computer systems. It uses a DC-DC converter to convert high voltage DC power to low voltage DC power so that the auxiliary battery uses the power. The power electronics controller transmits a signal to the traction battery pack to transfer energy to the inverter. The inverter transfers direct current power to alternating current power, which is received by the electric traction motor. Using alternate current power, the electric traction motor gets spun using the mechanism of spinning inverted magnetic poles, which shifts the mechanical energy from the motors to the wheels through a transmission. The wheel starts to spin and the vehicle will start to move if the driver presses the pedal. Now, what are the advantages of using an electric vehicle? Carbon dioxide emission per gallon of gasoline is 25 pounds, while for electric vehicles it's around 12.2 pounds of 10 kilowatt per hours, which is around 50% reduction of carbon dioxide. If electricity is gathered from solar energy, emissions drop by 95%. Other advantages of electric vehicles are very cheap fuels of 7 cents per kilowatt per hour, range of 110 to 300 miles per charge, and a higher acceleration compared to conventional vehicles. Lastly, in conclusion, electric vehicles are an extraordinary alternative to reduce carbon emissions released by cars that use gasoline and diesel by converting electricity to mechanical energy in the system of inverting magnetic poles. By 2050, we need to use $14.15 trillion, which could save $9.73 trillion of net savings and reduce 10.8 gigatons of CO2. This goal is being achieved as multiple major car industries such as Mercedes-Benz and Tesla are producing increased numbers of full electric vehicles. EV sales are also exponentially increasing as around 600,000 EVs were sold between 2022 and 2023. In 2023, the US alone reached more than 53,000 charging stations to aid in the customers' needs of charging their cars in different locations. We should continue this effort of using eco-friendly vehicles in order to save the world's environment for our future generations. Thank you.
Hi guys, today I'll be talking about solar farms, a plan to reverse global warming. So what is solar farms? A massive ramp up of solar power like that. Compared to small distributed clusters of rooftop panels, solar farms operate at a utility scale. Conventional power plant in the amount of electricity they produce, but dramatically different in emissions they produce. So why is it different? Usually found in deserts, on military bases, atop closed landfills, and floating reservoirs where they can also reduce evaporation. Silicon panel was accidentally discovered, but it was a good source of distributed power that could work in hot, humid, remote locations where batteries might fail and the grid would not reach. For statistic, it's number 8th most efficient. It would reduce 36.9 gigatons of carbon dioxide. Net cost would be 80.6 billion, but net saving would be $5.02 trillion, which would be beneficial after all. So how does it work? The silicon panels that make up a solar farm harvest the photons streaming to Earth from the sun, like that. And photons energizes electrons and create an electrical current. And the panel converts from light to voltage. So like this, it would kick off the electron, and that electron would convert to electricity, and it go from panels all the way to your house. Chemistry behind it. Solar farms curtails 94% of the carbon emissions they produce, that coal plants emit. Completely eliminate emissions of sulfur and nitrous oxide, mercury, and particulates. And those chemicals, beyond the basic ecosystem damage, they're also major contributors to outdoor air pollution that we don't want. And it's responsible for 3.7 million premature deaths. And these are the carbon footprint of coal and solar, and there is a big difference, as you can see. And why solar farms? Sun shines every day, providing us a virtually unlimited, clean, and free fuel at a price that never changes. And it's already on continuous decline in price, and it will soon become the least expensive renewable energy in the world, and is already the fastest growing. It's faster than creating a new coal, natural gas, or nuclear plants, and it already credits 220 million to 330 million tons of annual carbon dioxide savings, and they're less than 2% of the global electricity mix at present. So that would be residential solar panels, and that would be utility, which would be a lot cheaper. That's bibliography. Thank you.
Welcome to my presentation on sustainable aviation fuels. Today we'll explore how sustainable fuels and SAF work and how they can decrease our carbon emissions. Air travel is vital for global mobility and the economy. However, aviations produce carbon dioxide, nitrogen oxides, and black carbon. More than 3 billion plane tickets were sold in 2013, and there are 20,000 airplane services around the world. With the high demand for air transportation, aviation contributes significantly to pollution. Aviation is responsible for at least 2.5% of annual emissions, and as air travel will grow in the future, addressing these emissions is vital. One of the replacements for fossil fuels are sustainable aviation fuels, also called the SAF. SAF is a biofuel used to power aircraft that has similar properties to conventional jet fuel but with a smaller carbon footprint. Depending on the feedstock and technologies used to produce it, SAF can reduce life cycle greenhouse gas emissions dramatically compared to the conventional jet fuels. SAF can be made with a variety of technologies which use physical, biological, and chemical reactions to break down biomass and waste resources to recombine them into energy-dense hydrocarbons. It is estimated that 1 billion dry tons of biomass can be collected sustainably each year in the U.S., enough to produce 50 to 60 billion gallons of low-carbon biofuels. These resources include corn grain, oilseeds, agriculture residues, and more. This vast resource contains enough feedstock to meet the projected fuel demand of the U.S. aviation industry. Also, producing SAF from wet waste like sewage sludge reduces pollution pressure on watersheds while also keeping potent methane gas, a key contributor to climate change, out of the atmosphere. On average, SAF can reduce CO2 emissions by 80% compared to traditional jet fuels. A key to SAF's impact lies in its life cycle. When burnt, SAF still produce emissions similar to those emitted by fossil fuels, but unlike conventional jet fuels, which take fossil resources out of the ground and release previously stored carbon into the atmosphere, SAF primarily uses carbon that is part of the current carbon cycle in various feedstocks. This means that the CO2 emitted during an aircraft's flight is reabsorbed by the biomass used in the SAF production. Owing to its low production volume, SAF typically costs 2 to 5 times as much as traditional jet fuels, depending at any given time on the price of fossil jet fuel, the cost of renewable feedstocks, the relating processing costs, and more.
Good morning, Dr. C and my fellow classmates. This is Teddy. I'm here to talk about nuclear power is a suitable option to address global warming and climate change mitigation. To slow rapid climate change, the world must reduce greenhouse gas emissions to net zero. In 2018, 3/4 of global emissions came from energy production, especially fuel combustion. While an alternative to fossil fuels is nuclear. During operation, nuclear energy does not emit any greenhouse gases. Its carbon emissions come primarily from the mining and enrichment of uranium. Today, nuclear power helps avoid over 2 billion tons of CO2 emissions per year. That is equivalent of taking more than 400 million cars off the road every year. So how does a nuclear power plant work? This is the containment building where the nuclear reactors are housed. It is made of 2 meters thick reinforced concrete. Inside the containment building, a large tank called calandria, the heart of the nuclear reactors. This is the turbine generator building. It houses the turbine and generator. This is the controlling building for monitor and control the nuclear reactors. The fuel is naturally occur in uranium, then processed into small pellets. The pellets are sealed into metal tubes, which are welded to form a fuel bundle. The fuel bundles are then inserted in a large tank called calandria, which is the heart of the nuclear reactors. Typically, more than 200 of these rods are bundled together to form a fuel assembly. A reactor core is made up of a couple of hundred assemblies. In order to allow nuclear fission to proceed in a controlled manner, a controlled rod exists. The control rod can be moved up and down to control the fission rate of uranium. The calandria vessel is a cylindrical vessel housing lots of lattice tubes which are filled with heavy water moderator that flows around the fuel bundle. During the nuclear fission process, the heavy water flows around the fuel bundles. That's pumped through the reactor to a set of the steam generator where it transfers the heat to ordinary water. On the other hand, we need to pay attention to nuclear waste. When managed correctly, nuclear plants are processing powerful radioactive energy that needs to be disposed correctly to keep the environment and the people handling it safe. Modern nuclear plants keep waste to a minimum by recycling used fuel back into uranium-based and mixed oxide fuel, but 4% of nuclear waste can be processed and remains highly radioactive. Measured in half-life, or the time it takes for radioactive substance to reduce to half of its nuclear value, the time it takes for nuclear waste to neutralize varies wildly. Some common isotopes like strontium-90 have a half-life of around 30 years, but other powerful artificial nuclear isotopes like plutonium-239 have a half-life of over 20,000 years. In conclusion, despite minimal greenhouse gas emissions during operation, the nuclear plants might not be a comprehensive solution for global warming. Because of radioactive waste, it can remain hazardous for thousands of years and requires secure, long-term storage solutions, which are expensive and controversial. The future work of nuclear plants would primarily focus on addressing nuclear waste with innovative disposal technology to achieve sustainable and safe energy supply. Thank you.
Hi, I'm Matthew, and I'm talking about composting. Composting is the process where organic waste that may normally be thrown out, such as food waste and paper products, are naturally recycled and turned into fertile soil. Composting requires different types of organic material in order to be healthy, greens and browns. Greens are nitrogen-rich items such as fresh leaves and food scraps, and browns are carbon-rich items like sticks, paper, cardboard, and dead leaves. A healthy mix of greens and browns in composting is very important because the microbes that decompose the compost feed off of carbon and nitrogen. These microbes make possible a process known as aerobic decomposition. Aerobic decomposition, or decomposition in the presence of oxygen, is when microbes that require oxygen as fuel decompose and break down organic matter, creating gases such as carbon dioxide and a material known as humus. While carbon dioxide is bad for the environment, this process creates much less carbon dioxide than the alternative, which I will talk about later. Despite the negatives of the carbon dioxide, the material humus brings me to the first benefit of composting. The product of composting, humus, is a dark, nutrient-rich substance that looks like soil but isn't. Humus is an excellent fertilizer and can be used to grow very healthy, strong plants. The humus produced by aerobic decomposition is a great alternative to chemical fertilizers. Composting would allow farmers to use a natural source of nutrients for plants instead of having to rely on harsh chemical compounds that could end up in waterways and contaminate ecosystems. The use of natural fertilizer is very good for the environment and for health and is a great benefit of composting that doesn't show up when you're looking at the numbers and the statistics. In addition to creating a natural fertilizer, composting also reduces a lot of waste and keeps contaminant gases out of our atmospheres. Over 20% of waste in landfills is food waste. Composting would allow people to recycle their food waste instead of throwing it out, which would create much less trash in our landfills. When people don't compost, however, and organic waste is unfortunately thrown out, it will end up in piles in landfills. While in landfills, this organic matter will decompose, but it isn't the same aerobic decomposition that happens in composting. In the massive piles of trash in landfills, there isn't any oxygen, causing the waste to undergo anaerobic decomposition. Anaerobic decomposition is decomposition in the absence of oxygen, and this happens when microbes that don't require oxygen to survive decompose the matter. Through this process, methane gas and carbon dioxide gases are produced, which both cause severe damage to our atmospheres. By throwing out waste that could be composted, we are indirectly damaging our atmospheres even more. In these ways, reducing waste, reducing greenhouse gases, and creating natural fertilizer, compost reduces 2.28 gigatons of carbon dioxide every year. However, composting is expensive. It costs $63.7 billion. And to keep it running, it would cost even more, $60.8 billion in costs. The book, Drawdown, the most comprehensive plan ever proposed to reverse global warming, ranks compost as the 60th best way to reverse global warming, meaning that it may not be the most influential process, but it still makes a very big difference and should be pursued by more people. And this is my bibliography.
Hi, my name is Max, and today I'm going to talk about plastic recycling. Plastic pollution is one of the most serious environmental crises facing the world today, and it is really important for us to recycle plastics. Plastic recycling plays a crucial role in addressing the global plastic pollution crisis by reducing landfill waste, conserving natural resources, and protecting ecosystems. Between 1950 and 2015, over 90% of plastics were landfilled, incinerated, or leaked into the environment. The annual global production of plastic has now surpassed 380 million tons, contributing significantly to environmental pollution. Plastic recycling involves both mechanical recycling, where plastic waste is shredded and melted to create new products, and chemical recycling, which break down plastic into its chemical components such as monomers and hydrocarbons, allowing for creation of new plastics. Chemical recycling processes like pyrolysis and depolymerization hold promise for transforming plastic waste into valuable resources. For pyrolysis, plastics are heated to high temperature in the absence of oxygen, causing thermal decomposition, yielding smaller molecules like monomers and hydrocarbons. For depolymerization, polymers are broken down into their constituent monomers through chemical reactions such as hydrolysis or glycolysis, often with the aid of catalysts. Now, I'm going to talk about the benefits and challenges of plastic recycling. The environmental benefits of plastic recycling are substantial, including a reduced carbon footprint. Recycling 1 ton of plastic saves approximately 1.7 tons of CO2 emissions, and if we could recycle all plastic waste, we could potentially save up to 450 million metric tons of CO2 emissions annually. Economically, plastic recycling generates significant employment opportunities. For example, the recycling industry in the United States alone employs over 500,000 people. Utilizing recycled materials can lead to substantial cost saving for businesses. For instance, using recycled polyethylene terephthalate can be 30 to 40% cheaper than producing virgin PET, with net cost saving in the industry estimated to be in the billions of dollars globally. The recycled plastics market was valued at nearly $50 billion in 2020 and is expected to grow, driving market expansion and fostering innovation in sustainable technologies. The presence of non-recyclable materials hinders the recycling process and reduces the quality of recycled products. Many regions lack the necessary facilities and systems for efficient plastic recycling, posing a significant challenges to widespread adoption. A lack of consumer awareness about proper plastic disposal and recycling practices impedes recycling efforts, further complicating the issue. Lastly, step towards a sustainable future. Adopting circular economy models is crucial for a sustainable future. These models promote the efficient reuse and recycling of materials, minimizing waste generation. Investing in research and development of recycling technologies can accelerate the transition towards sustainable plastic management. Collaborative initiatives among industries, governments, and communities are essential for driving collective actions towards sustainable plastic recycling. Exploring the use of bio-based plastics and biodegradable alternatives offer innovative solutions to reduce the environmental impact of plastic waste. Implementing smart technologies for waste collection and sorting, such as AI and robotics, streamlines recycling processes and enhances efficiency. Leveraging digital platforms and interactive tools can boost consumer engagement and promote sustainable consumption behaviors. By embracing these strategies and fostering a culture of responsible plastic use of recycling, we can significantly mitigate the environmental impact of plastic waste, conserve valuable resources, and work towards a more sustainable and resource-efficient future. Every piece of plastic we recycle is a promise to our children and grandchildren for a brighter, cleaner future. Together, our small actions can create a legacy of hope and healing for our planet. Thank you for listening.
One of the most important global, political, and economic issues that faces us today is climate change. One idea for reversing climate change is tree intercropping, a method of farming that has benefits for the soil, the environment, and even the farmer who's incorporating these methods into their practices. Tree intercropping, at its core, is the practice of planting a diverse variety of plants and trees together on one plot of land. For example, if you drive through the Ardennes in France, you will often see poplar trees intercropped with wheat. The primary benefit of tree intercropping is the effect on the soil. This practice utilizes diversity to improve the soil health. The varying nutrients that come from planting multiple different species together make the soil far more sustained than it would be with only one type of plant. Healthier soil leads both to enhanced and faster crop growth. Also, in poor climate conditions, the coverage of the trees can create shade and wind protection, which further promotes healthier yields. A lot of these methods to fix global warming are hard to practice because they lose money, but this method actually helps farmers get more money. This method was actually discovered not for its environmental solutions, but simply because it's more profitable. This is due to a variety of reasons, such as lower input costs, improved market access, reduced risks, year-round income, and more. But, more importantly than money, it combats climate change. By planting trees alongside your other crops, you're both increasing the carbon content of the soil and absorbing more carbon dioxide from the atmosphere. The nutrients from a diverse environment can also mitigate the usage of pesticides or other chemical enhancers, which contribute significantly to climate change. Ultimately, Paul Hawken ranks this method 17th, saying it has the potential to save $22.1 billion and 17.2 gigatons of reduced carbon dioxide emissions. A simpler yet more effective solution is the planting of perennial staple crops. 89% of cultivated land is devoted to annually planted crops, which contribute far more towards climate change. Of the remaining perennial crops, only 116 million acres are used for perennial staple crops. Due to farming practices, annual crops cause a net release of carbon from the soil into the atmosphere every year. Because perennial crops don't have to be replanted every year, they emit far less carbon dioxide. Lands converted from annual crops to perennial crops sequester an average of 1.9 tons of carbon per acre every year. In terms of economic value, a perennial crop's yield is 2.4 times higher than an annual staples yield at 60% of the cost. Expanding the area growing perennial staple crops by 153 million acres would save 20.2 gigatons of carbon dioxide and $627 billion. Hawken ranks this idea 14th. While a simpler and potentially easier concept than tree intercropping, it would save billions of dollars and many gigatons of carbon from entering the atmosphere.
Thorium reactors are an exciting alternative to traditional uranium-fueled nuclear power plants that could serve as a relatively clean and environmentally friendly way to generate electricity in the shorter term as humanity makes the transition to renewable energy. Traditional nuclear power plants, or light water reactors, use uranium as fuel and generate energy through nuclear fission, in which the nucleus of a heavy atom like uranium-235 and LWRs absorbs a neutron and becomes unstable. The nucleus splits into two smaller nuclei, releasing energy in the form of heat and gamma radiation. This process releases more neutrons, which create a self-sustaining reaction by inducing fission in other nuclei. Thorium molten salt reactors use thorium-232 as a fuel source instead of U-235. Named after the Norse god of thunder, thorium-232 is not fissile itself, but upon absorbing a neutron will eventually decay into fissile U-233. In an MSR, thorium fuel is dissolved in a molten fluoride salt mixture, either lithium fluoride or beryllium lithium fluoride. This fuel circulates through a reactor core, where it releases energy that is used to boil water to drive a steam turbine and generate electricity. Thorium reactors come with a number of key advantages over LWRs. Perhaps most importantly, they are significantly safer. A thorium MSR cannot melt down and operates at lower pressures than an LWR, reducing the risk of a pressure-related failure. Because a liquid fuel is used, it can be easily drained into tanks below the reactor in case of emergency. Additionally, thorium MSRs produce less waste than LWRs, and the waste they produce is less hazardous. MSRs are also more efficient at energy production, since they operate at higher temperatures and efficiency scales with temperature. Thorium reactors come with a number of logistical benefits. Thorium is between 3 and 4 times more abundant than uranium on Earth, and is thus much easier and less environmentally taxing to mine and refine. Monzonite, the primary thorium-containing mineral ore, contains 6 to 7% thorium phosphate on average. It also contains valuable rare earth elements that are used in modern electronics, creating a bonus incentive to mine thorium. Thorium deposits are relatively evenly spread across the world, meaning that no country would control energy production. Additionally, thorium reactors produce much less of the fissile materials used in nuclear weapons than LWRs do, reducing the risks of nuclear proliferation. MSRs are also expected to be less expensive to build and will be economically viable at a smaller scale than LWRs, creating a more flexible means of energy production that could lead to more widespread adoption across the world. China is currently the world leader in thorium reactor development. Chinese scientists completed a test reactor in the Gobi Desert in August 2021 and plan to construct another reactor which would produce enough electricity to power over 100,000 homes. India, the UK, Japan, Canada, and the USA are all actively working on thorium reactor research as well. Since thorium energy is still early in development, it is difficult to assess the extent of its potential environmental benefits at this stage. However, many scientists believe that moving to low-carbon nuclear energy sources, while truly renewable energy sources like geothermal, solar, and wind power are improved upon and implemented, is a crucial step in moving towards a sustainable future.
Fast fashion and its environmental impact. Fast fashion is the mass production of low-priced but trendy clothing that moves quickly from design to retail stores in order to maximize profit. This term was first coined by the New York Times, describing Zara's mission to only take 15 days for a garment to go from design to distribution. Top brands include Zara, Forever 21, H&M, and Shein. These companies appeal to the public by advertising trendy styles at affordable prices. The fashion industry is the second largest polluter in the world, as it produces a large amount of waste and harmful pollutants. Manufacturing processes rely on chemicals that heavily pollute our air and water. Fast fashion is responsible for 10% of the world's total carbon emissions and 7% of the greenhouse gas emissions. Clothing production affects the environment at every stage. The apparel industry contributes to 3 billion metric tons of carbon dioxide equivalent. More than half of emissions come from 3 stages: fiber production, yarn preparation, and dyeing and finishing. These stages are driven by apparel production's reliance on hard coal and natural gas to generate electricity. Dyeing and finishing is the most energy-intensive stage because of wet processes that require extreme amounts of heated water. Cotton production contributes to 25% of global pesticides. Cellulosic fibers like viscose and acetate are only 8% of fashion fabrics but cause the chopping of millions of trees. Almost half of our clothes contain polyester, which is actually plastic. The material is versatile and cheap to manufacture, however, it cannot biodegrade. Polyester is obtained from oil. It is one of the most environmentally harmful fabrics. Moreover, the production of all synthetic fibers uses millions of barrels of oil each year and adds greenhouse gases due to their origin in petrochemicals. It takes about 700 gallons of water to grow enough fabric for one t-shirt. Each year, the fashion industry uses 1.5 trillion liters of water. At textile factories, toxic chemicals travel through pipes and pollute water systems. Water left over from the dyeing process is dumped into streams and rivers. This causes water to be undrinkable in some areas and also harms wildlife. 35% of all microplastics in the ocean come from the laundering of synthetic textiles. Specifically, the tanning process is the most toxic because chemicals such as formaldehyde and various oils are not biodegradable and contaminate water sources. After fabrics are dyed, they are cut and sewn into clothing. Unused textiles are thrown away. When clothing is produced with cheap fabric, it deteriorates faster and 85% ends up in landfills, which further increases the carbon emissions. How can we avoid fast fashion? Circular fashion is designed to minimize waste and make the most of resources. The goal is to keep resources in use for as long as possible, extracting value from them and then recovering materials at the end of their service life. It is a transformative solution to the fashion industry's challenges like climate change, pollution, and waste. In fact, using recycled polyester has the potential to reduce carbon emissions by 32%. Conscious consumerism is the practice of making informed purchasing decisions considering the environment. This movement encourages individuals to buy only what they need. Thrifting, reselling, and renting clothes are sustainable options to reuse and obtain them at lower prices. Another method that reduces the impact of fast fashion is expanding clothes' lifespan. For example, the simple practice of washing jeans less can save water from washing machines, reduce the expelling of microfibers, and reduce its carbon footprint by 18%. In conclusion, fast fashion's continuous cycle of overproduction and consumption harms the planet. To reduce carbon emissions, pollution, and excessive waste, the fashion industry must increase circular material flow, transition to renewable energy sources, and decrease excess waste. In the meantime, we can help the planet by making ethical choices. Less is always more.
Yeah, you talking about some Agua Cities, you heard me?
Amsterdam's pretty. They've got more bikes than people. I love the green city. They reduce the use of diesel. 3.3 trillion is the average savings per year for these cities. With 2.9 giggies is how much CO2 is saved from ozone depletion. That's carbon emission. Yeah. Memphis, Phoenix, and Orlando. Lots of cars here emit CO2. Up into the air it goes. This CO2 traps heat trying to exit our atmosphere. Then temperatures skyrocket, it's too hot. Starting to get severe.
Go take a walk, y'all.
This gotta stop, y'all. Guys, walkable cities are placed at number 54 in Paul Hawkins' book, Drawdown. 5% of trips currently made by car can be made by foot instead by 2050. So next time you think you need to take a car, take a walk. Walking isn't hard. Go get those steps in. You save money from a car if you just get those reps in. These types of cities are healthy for humans and the environment. Your life will feel more wealthy by using this enlightenment.
We want those walkable cities, y'all.
Next time y'all hear this song, think about those walkable cities.
There are cities where you don't need a car. You just walk.
Drake has fake abs.
BBL Drizzy. It's a good one.
Yeah.